Today's topic is chemical kinetics. So class, what we'll be studying in chemical kinetics, it simply says that branch of physical chemistry which deals with reaction rate and its mechanism. So class, what you are going to study in chemical kinetics? It deals with reaction rate and its mechanism. Class, types of reactions. Three types: very fast, very slow, and moderate reactions. Very fast ionic reactions, they require milliseconds to get completed. Milliseconds. So that's why they are not studied in chemical kinetics. Since the reaction is very fast, in the meantime we'll start or stopwatch, the reaction will be finally over. So since very fast, hence we do not study. Then very slow reactions such as corrosion reactions, which requires months and years to get completed. Therefore, class, we also do not study corrosion reactions. So what we study in chemical kinetics, it is your moderate reaction. So we'll be studying moderate reactions in chemical kinetics. Class, let us consider a reaction. Let us consider a reaction. Reaction is A giving me B. A is the reactant and B is the product, and hence if we draw a graph regarding their measurement of concentration with respect to time, concentration, class, what we find that concentration of A goes on decreasing with respect to time because A is a reactant that is going to be converted into product. So the concentration of A goes for decreasing with respect to time. This is molar concentration of A. Similarly, at the start of the reaction, product was 0, but as the reaction progresses, the concentration of B increases with respect to time. So this is a very simple graph. What it suggests? It suggests that A is a reactant, its concentration decreases with respect to time, and B is a product whose concentration increases with respect to time. So class, how do you define reaction rate? So reaction rate is defined as change in concentration of reactant or product with respect to time. So how we are going to write? For reactant, we will write minus delta A upon delta T. Class, is delta represents molar concentration. And class, since the rate can never be negative, so for reactants, we always take negative sign over here. This negative sign only indicates that concentration of A goes on decreasing with respect to time. And class, remember, rate is never negative. Suppose 5 moles of any substance get reduced to 2 moles. So final mole is 2, initial mole is 5. If we find delta, we find that value will come minus 3. And when minus 3 will be multiplied by this negative sign, it will give me positive sign. So that's why class, for the reactant, we always put negative sign in the expressions. And or either change in concentration of reactant or product with respect to time. So this is for the reactant, or for product we can write delta B upon delta T. So class, again, what is square bracket. Square bracket represents molar concentration. So increase in concentration of product with respect to time is your rate of reaction rate, or decrease in concentration of reactant with respect to time is your rate of reaction. In the next step, unit of reaction rate. Class, since this represents molar concentration, so it is mole upon liter divided by time. So mole liter inverse time inverse. So this is very important expression. For reactants, we always use minus delta A upon delta T, and for the product we always use delta B upon delta T, and unit of reaction rate is given as mole liter inverse time inverse. Very important unit. Please don't forget. In the next topic, we are going to find out types of reaction rate. It can be measured in two ways: average rate and instantaneous rate. Plus, average rate. When the reaction rate is measured over long time interval, it is called average rate. We started a reaction at 2 o'clock and we are finally ending it at 5 o'clock. So 3 hours have been passed. If we take the entire 3 hours into consideration, that reaction rate will be the average rate. How to write the expression? RAV. Remember class, A was your reactant. So RAV will be equal to A2 minus A1. Again negative sign because it's a reactant, upon T2 minus T1, or for product we can write B2 minus B1 upon T2 minus T1. So when the reaction rate is measured, over long time interval, it gives us average rate. Class, we can have a numerical on this. 5 moles of HI were reduced to 3 moles in 2 hours. Find RAV. Class, since HI is a reactant, so we'll use HI final minus HI initial upon time taken. So RAV will be equal to HI final minus HI initial upon time taken, and a negative sign here. The next step, final concentration is 3 moles. Initial concentration was 5 moles upon time period 2 hours. So class 3 minus 5 will give me minus 2, and minus 2 multiplied by negative sign will give me positive 2. So we'll get 2 by 2. So we can write 1 mole hour inverse. If we divide by 60, we get the value in minute inverse. If we further divide the value by 60, we get in the second inverse. So class, here the answer is 1 mole hour inverse. So this is your average rate. Now we'll move to instantaneous rate. Instantaneous rate. Class, concentrate on the word instantaneous. At any given instant. So when the reaction rate is measured at a particular time or at a particular instant, it is called instantaneous rate. So rate measured at a particular time, it is called instantaneous rate. Suppose let us take one example. What is the rate at 2 o'clock? Exactly at 2 o'clock, what was the rate? So that rate will give you the instantaneous rate. The last topic we discussed that what was the rate between 2 hours. So that was your average rate. We are finding the reaction rate for the entire time period. But in this case, instantaneous rate, we are finding the reaction rate at a particular time. So class, how to find this instantaneous rate? We'll have to draw a graph. So I am going to rub this average rate. Again, we'll take up the same reaction. A giving me B, and let me draw a graph first. This is your concentration, this is your time. For reactant, we got the graph like this. So class, suppose if you want to find the instantaneous rate here, whatever may be the time. Okay, so let us start that we have started the reaction at 3 o'clock, we are ending at 5 o'clock. So these are the time ranges between 3 to 5. So what is the rate exactly at 4, 5? So what to do? So we'll just taking this time into consideration, we'll come here and we'll make a tangent over here responding to this time on x-axis as well as y-axis. So this is a tangent for this particular time. So how to write instantaneous rate? Instantaneous rate will be equal to, see, this will give you delta x and this will give you delta t. So instantaneous rate can be measured by delta x upon delta t. So this is a way to find out instantaneous rate graphically. I repeat again, let us take a concentration A here. So this is a molar concentration of A. With respect to time, the concentration goes on decreasing, and suppose we want to find out instantaneous rate at a particular time. So for taking this time as a standard, we'll come here and we'll make a tangent over here corresponding to this time. This will give me delta x, that is change in concentration, and this will give me delta t, and ultimately we'll be able to find out instantaneous rate graphically. So this is the way to find instantaneous rate graphically. Class, very important, instantaneous rate also. In the next step, we are going to take writing instantaneous rate expressions. So class, how to write instantaneous rate expressions? Let us take an example over here. We will consider decomposition of hydrogen peroxide into water and oxygen. Class, if you consider only these two, see, the time required by 2 moles of H2O2 to decompose is same as time required by 1 mole formation of O2 gas. I repeat again, the time required by 2 moles of H2O2 gas to decompose is the same time, in the same time 1 mole of O2 gas is formed. So class, can I say that rate of formation of O2 is half of the decomposition of H2O2? I repeat again, time required by hydrogen peroxide for 2 moles to decompose is the time required by O2 molecule for 1 mole to be formed. So rate of formation of O2 is half of the decomposition of H2O2, obviously, because in the same time 2 moles of H2O2 breaks, but in the same time only 1 mole of O2 is formed. So therefore we can write the expression as follows. See here, H2O2 is a reactant. So class, what we discussed the same thing, that rate of formation of O2 is half of the decomposition of H2O2. Similarly, class, if we consider these two products, time required by formation of 1 mole of O2 is equal to time required by formation of 2 moles of H2O. So class, in the meantime, when 2 moles of H2O decompose, only 1 mole of O2 is formed. So for these two, we can write another expression here. Since it's a product, that I am not writing negative sign here. Class, the time required by formation of 1 mole of O2 is just half of the decomposition of H2O. So O2 by delta T equal to this, O2 by delta T equal to this. So these three are equal. So I can write final expression here. Final expression comes minus H2O2 upon 2 delta T equals to delta H2O upon 2 delta T equals to delta O2 upon delta T. So class, this becomes my instantaneous rate law expression for the above reaction H2O2, twice H2O2 giving me twice H2O plus O2. Similarly class, okay, before moving to next example, class, observe the reaction carefully. See, the stoichiometry of H2O2 is 2, similarly stoichiometry of water is 2 and stoichiometry of O2 is 1. If we consider this reaction with this expression, what we find that we have simply divided these two by their respective stoichiometry, and O2, since there is 1, so divided by 1. So the catch point for writing instantaneous rate expression is that what you do, you simply divide by the stoichiometry of the balance equation. So in this way you can find out the instantaneous rate expression. And class, please remember, this is instantaneous rate law expression, not rate law expression. There is basic difference between instantaneous rate law expression and rate law expression. We have not yet taken rate law expression, we have taken instantaneous rate law expression, and instantaneous rate law expression we are simply dividing by the stoichiometry. Class, let's have another example how to write instantaneous rate expression. Just see. Let us take Haber's process of ammonia, N2G plus 3H2G giving me 2 ammonia G. If you want to write the rate instantaneous rate expression for this, class, N2 is the reactant, so delta N2 upon delta T, remember the negative sign, stoichiometry is 1, so I am writing it is obviously 1, equals to delta H2, again hydrogen is the reactant, so negative sign upon stoichiometry is 3, so 3 delta T equals to delta ammonia upon 2 delta T. So class, you can very well find out that what I have done, I have simply divided the stoichiometry by, we have simply divided the concentration term by their respective stoichiometry. So this is the catch point to write instantaneous rate law expression. And class, of very important point to remember, what is that? Rate of reaction is always given by that reactant or product having stoichiometry unity. So if you consider this reaction, stoichiometry of nitrogen is 1, so nitrogen will be giving us the rate of reaction. Similarly, let us talk here. Here O2 has stoichiometry 1, so rate of reaction will be given by oxygen here. So class, remember very well that rate of reaction is always given by that reactant or product having stoichiometry unity. Class, sometimes students ask, sir, in the entire reaction, let us take 3A plus 5B giving me 2C. Here, no one is having stoichiometry unity, sir. What will we do? In that situation, class, remember, you can take any one, either A, B or C, but suppose if you want to take A as a rate of reaction, so what you do? You divide the entire reaction by 3, so we get A by 5 by 3B, 2 by 3C. Now I can very well find out my instantaneous rate law expression. So class, remember, rate of reaction is always given by that reactant or product having stoichiometry unity. Class, in the next step, we are going to we are going to do a numerical based on instantaneous rate law expression. See, at any instant, rate of reaction was found to be 3 into 10 to the power minus 5 mole liter inverse second inverse for the reaction. And reaction has also been given to you, N2 plus 3H2 giving me 2 ammonia. Class, rate of reaction has been given to me, and now what is being asked? Find rate of decomposition of N2 and H2 during same time, and number 2, find rate of formation of ammonia at that instant. So at a particular time, rate of reaction was given to me 3 into 10 to the power minus 5 mole liter inverse second inverse for Haber-Spalzer ammonia, and now question is being asked, find rate of decomposition of N2 and hydrogen during same time, and find rate of formation of ammonia at that time or at that instant. So class, my first one will be to write down rate law, instantaneous rate expression for this. So delta N2 by delta T, negative sign, equals to delta H2 by 3 delta T, again negative sign, equals to delta ammonia upon 2 delta T. Class, we have just understood that rate of reaction is given by that species having stoichiometry unity. So nitrogen has stoichiometry unity. So we'll write our first answer, rate of decomposition of nitrogen, same rate, 3 into 10 to the power minus 5 mole liter inverse second inverse. Once we got rate of decomposition of nitrogen, we are going to equate these two equations to get hydrogen also. Class, I have already told you that rate of reaction can never be negative. So while finding the rate of reaction, we will never use this negative sign. Just forget this negative sign. So delta N2 upon delta T equals to delta H2 upon 3 delta T. N2 by delta T, the value is given 3 into 10 to the power minus 5, and if you cross multiply, we get here multiplied by 3 to give me delta H2 by delta T. So the value comes 9 into 10 to the power minus 5 mole liter inverse second inverse. Then class, this was answer number 1, this is answer number 2, 9 into 10 to minus 5 mole liter second inverse. Then I am going to equate nitrogen and ammonia. Equals to delta ammonia upon 2 delta T plus rate of nitrogen, we all know, 3 into 10 to the power minus 5, and now it should be cross multiplied by 2 to get delta ammonia upon delta T. The value comes 6 into 10 to the power minus 5 mole liter inverse second. So class, this is the way you can very well find out numericals on instantaneous rate. I have given one example. So class, that completes our types of reaction rate. We have studied two types today. One was your average rate and second was your instantaneous rate.